Hello, everyone. Welcome to our webinar on exploring the technology behind surround view cameras. I'm Jason Montgomery, your host for today's webinar, and I'd like to welcome our presenter, Radhika Arora, Director, Autonomous Driving. Radhika Arora is a proven leader in business development and strategy with an impressive track record of increasing profits and expanding market share. Radhika currently works at Semiconductor as Director, Autonomous Driving. She drives the strategy for self-driving cars with a focus on image sensors. Her efforts have led to onsemi having far-reaching impacts with key design wins. Prior to that, Radhika served as Product Line Manager, Image Sensor Group. She managed the Internet of Things scanning product line, growing it into a critical and highly profitable segment for the company. Radhika also founded a nonprofit organization, Uncharged. The organization focuses on enriching lives and improving productivity in rural India through means of alternative and sustainable energy solutions. Folks, please be sure to use your Q&A widget to submit your questions. If we don't get through all your questions during the Q&A session, then a reply will be sent via email. And with that, let's get started. Radhika, over to you.
Jason, thank you for that introduction. Good morning, good afternoon, good evening, depending on which part of the world you're dialing in from. I'll be taking you through the next 45 minutes of information around surround view cameras. And we'll be taking questions at the end of my presentation. So let's jump right into it. In terms of the agenda, we're going to keep it simple. A few key points to cover in the webinar today. I'll be talking about the surround view camera market and trends. We'll get into understanding some of the challenges that are faced by OEMs in the surround view camera space. I'll go into depth on the camera technology that sits behind surround view systems, and then we'll wrap it up with some key takeaways. All right, so what is a surround view camera system? Automotive surround view systems refer to an intelligent camera system which provides a complete 360-degree view of the vehicle on an LCD, or now an OLED screen as well, that is placed on the dashboard in a vehicle. These systems play an important role in assisting the driver during parking or maneuvering of the vehicle. They also have other benefits, such as enabling the driver to get a sharp view on all sides, removing the blind spots, lowering distractions of the driver, and essentially overall improving traffic safety. Now, over the years, these systems have evolved from low-resolution cameras, moving and progressing towards higher resolution cameras, providing a real-time bird's-eye view of the vehicle and its surroundings. These advantages have significantly contributed to the overall installation of these systems and is representative in this feature showing up in a growing number of cars. Also, advancements in automotive advanced driver systems as ADAS technologies have led to an increase in the sale of automotive surround view systems. Manufacturers have increased research and development to develop these systems with much higher accuracy and much more richer and advanced features, which we'll talk about in a little bit here. So just as an example, they're now offering sonar-based systems that judge the distance between obstacles and give the users a warning when an object comes near another car or another object. All right, so what you're looking at on the screen here is essentially a basic surround view camera system. Now, the 360 camera view utilizes several cars that are located around the vehicle to create a bird's eye view of the vehicle. The normal 360-degree system is comprised of 4 cameras. The exact location of the camera can vary, but generally there's a camera in the front bumper or grille, under the side mirrors, and in the rear of the vehicle. The camera in the rear of the vehicle can be located in the lift gate, the tailgate, the deck lid, or the rear bumper. There are also more advanced 360-degree camera view systems that use a camera on each side of the front bumper cover or multiple cameras for the rear view. These additional cameras can give more varied views, such as a view of the intersection that is being approached or the blind spot when backing out of a parking space. The cameras might have the ability to view a large area, so most of the cameras will typically have a wide-angle lens. The cameras on the side of the vehicle must have the ability to see the whole side of the vehicle from the front bumper to the rear bumper. The cameras on the front and rear need to be able to see far to the left and right of the car. Many OEMs have a disclaimer warning that there may be blind spots in the camera viewing areas, and some of these blind spots are by design and cannot be adjusted. So the market for surround view cameras is a fast-growing one. We are looking at a CAGR of about 31% across 5 years. And this is something that's been reported by multiple marketing research firms, well-established ones. And it's one of the contributing factors also is the fact that we'll have more rules and regulations, ones that have already been instated and more that are in the works. So just as an example, when we look at the rear view camera market, today it's mandated in the US. Actually, since 2018, all the model cars being introduced in the US market mandate the integration of a rear view camera. So this rapid push to adopt a technology solution is also due to the fact that 31% of the fatalities being young children and under 8 years of age happen to be in the blind spot behind a car on a mirror-only vehicle. Rear view cameras have now passed the 50% point on cars that have them, available either as standard equipment or options. So for a car with a center console display, the cameras are only, say, about $40 to $50 per vehicle adder. For those without a display, the systems have been opting on embedding displays in the rear view mirror, and this with the camera adds on another $135 to $165 per vehicle at the OEM level. When looking at some of the driving factors that sit behind the growth in this market segment, OLED displays are a big factor. There are more and more people who are looking for higher displays, larger size, and quality. Now, OLED displays are gradually emerging as the most preferred display panel technology among automotive companies such as GM, Audi, Toyota, Volkswagen, Mercedes. A couple of examples here. The Mercedes-Benz is set to launch its new cars with OLED panels developed by LG Display in dashboards and rear seat monitors starting this year. Vehicles with OLED displays are, we continuously see them shown at various exhibitions almost regularly, but the Mercedes-Benz has become the first automaker to utilize OLEDs in its consumer models. Another example is Audi, which features rear view cameras connected with 7-inch OLED monitors. This arrangement ensures that different angles and views are displayed on the OLED monitors inside the vehicle, ensuring better visibility, picture quality, and sharpness that you'd not typically find on a LCD screen. And this is also a unique selling proposition for vehicles. Something else to highlight here is safety. It is a significant differentiator when selling vehicles from the OEM standpoint. The availability of crash test data and the ability to avoid minor dents and dings as well as serious accidents has become a real factor in consumers' choice of vehicles. This has changed how automakers are marketing these new features. With consumers prepared to pay for safety, features like blind spot monitoring, lane departure monitoring are proving to be more compelling to justify the presence of a central LCD or OLED infotainment system than paying for the upgrade to get a better radio or navigation system. Previous additions to basic car models are increasingly centered on enabling better visibility and safety and are proving to be better economic propositions for the car makers as well. There's more on the horizon as the cost of implementing safety features makes it possible to deliver them in more mainstream models. More and more video will be used to deliver capabilities like night vision and auto brightening and darkening to improve visibility, for example, and the windshield will become yet another display for diagnostic data. The ability to deliver reliable, easy to integrate, and cost-effective video solutions will be key enablers of the next generation of camera features, which are increasingly driving safety and ultimately consumer demand for new vehicles. So looking at some of the features for surround view cameras, I mentioned a very basic surround view camera system at the beginning with the 4 cameras. There is rear view that can be put in the same category. There are new use cases like mirror replacement. I'll talk more about that later. There is a whole new category with automating parking as well as valet assist, trailer reversing, blind spot warning, structure promotion, augmented reality, highway driving. We'll get into some of these use cases in the next few slides where I'll highlight the uniqueness and differentiation in terms of the camera technology. So starting with the basic surround view system, what you're looking at the screen here is a basic surround view system that uses, say, about 4 cameras. We've seen that number growing in recent times, going up to 6 cameras of surround view systems. And when we look at some of the early designs we've seen for level 4 autonomy, we are seeing surround view cameras all across the car where the number of cameras per system can be 15 and beyond. So here the images from each camera are pieced together to create one single image. The image is then sent to the screen, which will display the 360-degree camera view. And depending on the complexity of the 360-degree camera view system, other systems may also provide input. This system can tie in with park assist sensors or other collision avoidance systems such as rear cross traffic. some systems are able to detect a moving object in the 360-degree view, such as a ball rolling or a shopping cart that may be moving towards the vehicle. And understanding how the system functions can greatly shorten the diagnostic times. And knowing what part of the system to test will help prevent installing parts that don't actually fix the problem. The body shapes and size of different vehicles dictates the camera installation points, and each vehicle requires a unique setup of the system. The cameras are furnished with lenses with an extreme wide-angle field of view, going up to 180 degrees, which basically cause issues like fisheye distortions in the output video. Furthermore, each camera captures the surroundings from the perspective defined by the installation point specifically. And that perspective must be transformed into perspectives suitable for selected views. The surround view camera system is also responsible for removing the lens distortions and corrects the perspectives of these 4 high-resolution input video streams, and then stitch the corrected video images in a single display of the vehicle surroundings. As you can imagine, the correct image stitching is very challenging due to the overlapping of the scenes captured by the cameras as a result of these extreme wide-angle field of view lenses. Now, the amount of video data that must be processed in real time is big and requires dedicated DDR2 or DDR3 SDRAM memory devices. The interface between the surround view systems processing unit and the memory must ensure data throughputs that reach a gigabyte per second in systems, as an example, with a 1280 by 800 resolution running at about 30 frames per second. The surround view systems must be easy to use and capable to solve a lot of challenges, including quick system adoption to different car types, body shapes that dictate the camera installation points. There are also static and dynamic system calibrations that need to be taken into account. There should be an easy way to explore between different viewing options. Also with a mix of camera sensors, the lenses, the camera interfaces, the interfacing with other ECUs, HMI control, etc., can add to complexity very quickly. The system's cameras must be synchronized to avoid the appearance of image tearing or other unwanted display artifacts. Now, these cameras may be exposed to extremely different lighting conditions. To give an example, there could be 2 cameras that might be in direct sunlight, and the other 2 that might be in a shadow, such as lighting conditions must be properly equalized. If you have one set of cameras that are completely saturated while the others that are in dark, it could lead to a unbalanced image, thereby missing objects or missing the important components that are necessary to make critical decisions. New cameras and interfaces are developed quickly around these surround view systems, so it must be imperative to keep them flexible to keep up with the pace of these emerging and evolving image sensor technologies as well. So let's look at another example of a surround view system. It's mirror replacement. Vehicles without glass mirrors have long been proposed by stylists and engineers wanting sleeker looks and improved safety as well. And eliminating the mirrors can also help with fuel efficiency because the assemblies are smaller, they cut the wind better. So with camera monitoring systems as an emerging technology, that could be an eventual replacement for mirrors. But at this moment in time, they're not entirely welcome in North America. There are some companies that offer a compromise. Some countries in Europe and Asia allow camera monitoring systems to replace mirrors, but safety regulations in the US and Canada specifically require vehicles to have inside mirrors as well as outside driver side mirrors to complement a camera system. So one of the offerings from a tier one is an inside mirror that can switch to a video display mode. So outside you have a side view mirror with a camera mounted to it that sends a video feed to a screen inside that car located on the driver or passenger side, the A pillar as it's called. The camera is mounted beyond the widest point of the vehicle to cut out the blind spots. And some other options, only compliant in Europe and Japan as of now, they eliminate the outside mirror entirely in favor of a camera feed to the video screen. It is estimated that just 0.5% of vehicles going globally will have the technology by 2025. That's mainly because the camera monitors are legal in only a handful of countries as of today. A few years back, the Transport Canada group published a proposed amendment to motor vehicle safety regulations schedule requesting feedback on this as well. And there were really no stakeholders that supported their proposal completely. So the regulatory side continues to be a challenge in North America for a few years, but we're seeing more widespread adoption of it in the European and Asian markets. So an advantage, a couple of advantages for replacing the mirrors with the cameras include having the opportunity to be safer from a visibility point of view because you're getting a larger field of view. Glass mirrors have a 12-degree field of view, while camera monitoring systems can provide a 50-degree field of view. We've seen an example from a system that's out there. We've seen improved coefficient of drag. In this particular case, it was 0.27 for a Eurospec version, which basically translates to about 3 miles of range at higher highway speeds. It results in a reduced total vehicle width. In the case of Audi e-tron, it was about 5.9 inches. So definitely some advantages there. It is changing user behavior and a new way of interpreting the surroundings around you. There is some disadvantage, specifically coming in at nighttime, which causes the quality to degrade a bit. And then there is, of course, the challenge of keeping the camera free of dirt, debris, water droplets, but there are some OEMs that have come up with some unique features on that front to overcome these challenges. Moving on to augmented reality. This is another unique feature that we've seen offered by a particular OEM. Here in this case, it's GM. It's essentially creating visibility. In this case, there is a trailer that's put behind the vehicle. It's a powerful part for augmented realities in cars which often suffer from obstructed visibility. It uses a camera view from the back of the trailer that's superimposed over the actual view via the dashboard screen to make the trailer that's being pulled basically seem as if it's vanished. Going the other direction, you can also have some AR tricks to make the front of a vehicle disappear, so the tricky terrain that you're traversing becomes more visible. So what you're seeing on the screen here, I've called it the perils of parking because I personally have faced some of these challenges, be it in the form of parallel parking or trying to squeeze my car in a really tight spot in between two cars. The last image I'm showing on the bottom right, just a disclaimer, no, it has not happened with me, and I hope it doesn't. So that is an extreme case, but drives the point of the issues and challenges we go through in parking and time spots, and how automotive park assist can be a great advantage. Going into that, when it comes to parallel parking, most drivers require about 6 feet more space than is necessary in order to fit into a space. The car doesn't completely drive itself when it's in park assist. And the onboard computer system does a lot of the calculation steering involved. In parallel parking, as soon as the system has been engaged, the car pulls forward into position beside the car or in front of the space, issuing a signal to the driver. The onboard computer uses powerful steering systems to turn the wheel, move the car into the parking space. This kind of a system uses sensors that are placed around the vehicle to prevent it from hitting objects around it. Different models and systems have different placements of sensors around the vehicle. Some act as transmitters and others as receivers. Signals are transmitted by the vehicle and they bounce back off objects so that the computer can then calculate the location of the objects in relation to the vehicle. A lot of them use cameras instead of sensors, while there is also an option using radar systems to detect these objects. So surveys of drivers consistently show parallel parking to be amongst the most anxiety-inducing experiences we have behind the wheel. Moreover, low-speed car accidents, such as those that occur in parking maneuvers, are considered to be a source of serious injuries that include concussions and other soft tissue injuries as well. Parking assist features can help avoid these accidents, and consumers just love the convenience and peace of mind that these capabilities provide. Based on a survey from the AAA newsroom, there's supposed to be 81% fewer curb strikes than drivers parking without assistance, 47% fewer maneuvers than unassisted drivers, and 10% faster than a driver parking manually. Okay, so now getting into the image sense of the camera side, we've seen different combinations and implementations of the camera at the OEM side. So a basic form of this is using a raw image stream. That means just the pixel array. The camera outputs a combined or a separate raw image from the multiple cameras in the system. The advantage of an implementation of that nature would be a compact camera, so it's smaller in size because you just have the basic image sensor. And as a result, it would also have the least amount of heat. Another implementation would be that we have the pixel array plus the color pipe integrated, but there's going to be no spatial transform engine or no kind of overlays that are integrated in the camera system. There is still the option of you have a processed image that's going out, plus a SerDes, and it's a high definition image. In this kind of an implementation, it removes the ISP burden from the ECU or the head unit. It simplifies the IQ tuning from the OEM side, and that's because you've got the color pipe integrated in the image, so what you're getting out of the camera is with the color processing already taken care of. And this is a close interaction that happens between camera vendors and the end OEMs in order to customize the image per the unique requirements of the various vehicle manufacturers. From an OEM perspective, it also allows for flexible sourcing. And then there is what we call the all-inclusive camera category, where you've got the pixel array, the color pipe, plus the SDE, the overlays, the SerDes, all integrated into one comprehensive camera unit. There is also a new emerging technology that's coming up, which is called the smart camera category. And in this case, there is an addition to machine vision. And having some kind of basic machine vision algorithm or neural net in the camera head itself helps improve detection and reaction latency. So it's a new category that's emerging in this space. Moving along, looking at the motivation for the basic camera architecture, what you're seeing on the screen here is the first one is a basic camera fed into a head unit. So the basic camera is the image sensor, the color pipe, the SerDes, being fed into a head unit, which includes the deserializer, some kind of a controller with deep DWAP overlay, which in turn is fed into the head unit. This is a single camera part or multiple cameras. With the integration of the color pipe, it helps reduce the price. Integration of the ISP and sensor in the camera reduces overall system integration problems. The ISP in the ECU can limit the sensor choices for the OEM, and the source camera and ECU kept separate. From the OEM standpoint, they have the flexibility in terms of picking their sensor supplier. So getting into generating a surround view from multiple cameras, geometric alignment that helps correct the fisheye distortion for input video frames, converts them to a common bird's eye perspective. This step includes both fisheye lens distortion correction as well as perspective transformation. Then there's the whole idea of photometric alignment. It's an important piece which corrects the brightness, the color mismatch between adjacent views to achieve seamless stitching. Due to the difference in scene illumination, camera auto exposure, auto white balance, color, brightness of the same object captured by different cameras can all be quite different. As a result, the stitched composite image can have noticeable differences between adjacent views. So the goal of photometric alignment for a surround view system is to match the overall brightness and color of different views such that the composite views appears as if it were taken by a single camera. So spatial transformation of an image is a geometric transformation of the image coordinate system. It is necessary to perform a spatial transformation to align the images that were taken at different times or with different sensors, correct images for lens distortion, correct effects of camera orientation, image morphing, and other special effects. So the next few images that I'm going to take you through, the first one is what the default image looks like. The second one shows you what it would be if you're zooming into that particular image. All options available on surround view cameras. If you can tilt the image about 45 degrees, you can rotate the image 45 degrees. You can use it in pan mode or have the option of adding arcs. Some offer as much as 10 arcs, 20 lines, offers the ability to anti-alias. There are general curves that can be created and superimposed on the images. And keep in mind, in this case, in all of these examples, the camera is not physically changed position. All that has changed is the spatial transform engine configuration. All right, so now getting into some of the challenges in the automotive imaging world. When we look at real-world scenery, it often is in excess of 120 to 140 dB in terms of dynamic range. By dynamic range, what I mean is when you're looking at a single frame where you could have a lot of sunlight that's hitting the frame, plus that frame being in shadow as well. There is also the requirement of the sensor operating in a wide temperature range from minus 40 C to 105 C. You could be in the Sahara Desert or you could be up in the North Pole driving this car. Then there is also the issue of traffic lights, LED sign flicker artifacts that can be a big hindrance in viewing applications. Also, there are requirements that are released by Euro NCAP that which have specific requirements to detect a pedestrian or bicyclist that comes more in the ADAS category. The next image that you're seeing on the screen here, just to reinforce the point of a high dynamic range scene. On the left-hand side of the screen, you're seeing a tunnel. This image is taken with a sensor that does not have high dynamic range. So right at the exit point of this tunnel, you're seeing that the vehicle is hit by a lot of sunlight getting right out of the tunnel. So part of the car is covered in light while you have the rear of the car that is still in the shadow. And overall, the image is completely saturated. On the right-hand side of the screen is the image taken with a high dynamic range sensor, where you can see the balance and you can see clarity in the images. You can see the objects, you can see the traffic lights getting out, which again enforces the point of the requirement for at least 120 dB minimum, with the requirements only going up. The next one is on pulsed light flicker challenges seen in high dynamic range scenes. In automotive lighting, LEDs are used with pulse width modulation at low frequencies down to about 90 hertz with low duty cycles, down to 5 to 10%. Now, to capture the light source, camera needs to guarantee a single exposure can capture a single pulse, even with the exposure set to more than the LED period. In this case, with a 90 hertz frequency, you have to set it to 11 milliseconds. Now, the minute you're exposing that frame for 11 milliseconds, in bright conditions, you want to shorten the integration times that are typically used. The trade-off with that is that with a short integration time, you will then miss the on cycle of the LED pulse from frame to frame, which then shows up as flicker. So this slide is showing the different kinds of lights that cameras have to capture. The first image is holiday lights. They shouldn't be flickering, but because of this LED frequency differences, they do. Street lamps should not be flickering, or in the last image that you're seeing, tail lights or blinkers. You cannot tell the difference because we missed some pulses of the LEDs, which in turn result in the shape not being correctly observed. So you cannot tell whether it's just the tail light that's turned on or it's a blinker indicating whether it's a left or a right turn. So this is a comparison of regular and LFM operation images. The first one shows the 100 miles an hour sign distorted, so you cannot really read what that sign indicates. And similarly, the middle and the third image as well, where the full signs are broken, leading to misrepresentation. All right, moving along to some of the pixel architectures, just going down a level deeper now, looking at pixel architectures used in camera technology. There are two competing technologies in the market today. There's super exposure pixel and a split pixel technology. So when we look at the split pixel technology, it has a fundamental problem in spatial separation of two exposures in an image. Example, the center of exposure within the pixel is shifted. Now, split pixel basically translates to a big photodiode and a small photodiode that are used to capture the photons. Now, with the center of the exposure that's shifted, as a result, all the images where there is transition from bright to dark would experience all kinds of artifacts. It could be sawtooth color artifacts along the edges that then require special filtering, thus degrading the information. This also creates a lot of problems for stereo cameras that rely on all edges being same for the left and the right images. The super exposure pixel technology helps eliminate a lot of these challenges that are seen. Split pixel has the inflexible adjustment of exposures as well, due to the fact that one of the optical ratios is fixed between the large and the small photodiode. The super exposure approach provides flexible clock-controlled exposures. Result is that super exposure-based sensors provide better SNRs at exposure transitions while still maintaining a high dynamic range. Split pixel technology also shows higher fixed pattern noise. due to variability of the optical ratios among pixels. So within the die and from die to die, there is a lot of variation that's seen. It requires per pixel calibration to fix it. Super exposure uses one common optical path. Thus, the optical factor is the same, resulting in a low PRNU across all exposures. Split pixel technology also requires the ratios and the crosstalks to have a lot of spectral dependence. Example, the large photodiode and the small photodiode crosstalks change with the light angles, the light spectra, thus generating different signal ratios as well as some color shading across the array. Split pixel also has the disadvantage that shrinking it beyond or below 3 micron size, example, the two photodiodes have multiple gates, so it proposes a challenge. With a super exposure technology, to get to a smaller size of 1 micron, going down as low as 1 micron is a lot easier to do. So in the interest of time, I'm going to take over some of the pixel-specific technologies, but I want to make a couple key points in the last few minutes I have here, and that is on functional safety. This is something that is starting to become a must-have feature as opposed to a nice-to-have feature. And from ON Semiconductor's automotive imaging portfolio, we develop all our sensors as safety elements out of context. The safety case is based on a combination of independent functional safety analysis as well as industry's best practices. The image sensors are used in a wide range of applications, develop of safety cases based on road vehicles as defined by the ISO 2626 standard. The safety case for this product family supports the use of image sensors in a wide array of applications. It helps with, basically our motto is safety starts at the sensor. It helps from when we are looking at a system standpoint, the time for the system to reach a safe state is a key safety metric. Some faults can be difficult or impossible to detect at the system level. It is also important or more efficient to detect these faults in the sensor than it is with post-processing. Okay, so jumping to some key takeaways. The worldwide market for automotive surround view systems is a fast-growing market, slated to be about $4.2 billion in 2024. The display size and quality as seen in vehicles is a major buying factor. For surround view cameras, we are seeing a general trend to move to a minimum of 2 megapixel in resolution. Image sensor pixel technology like super exposures are leading the market in both HDR and LFM performance. ASO functionality is starting to be seen as a must-have than a nice-to-have feature. Just to end with ON Semiconductor's offerings in the surround view camera space, we have our section on the website that's dedicated to this. Besides image sensors, we also have another broad range of offerings. I've provided a link to these slides, which will be provided later, that you can click on to learn more about what ON Semiconductor has in its portfolio. which is a comprehensive suite of components to build a complete surround view camera system. Thank you. And with that, I'm going to pass it back to our host, Jason, who'll open it up to questions.
Radhika, thank you for providing a great overview. Let's dive a little bit deeper and begin our Q&A session. And as a reminder to any attendees, if you have any questions that you would like answered, now is a great time to go to your Q&A widget and submit those now. The first question that we have is, what is driving the trend for higher resolution sensors?
So if you remember at the beginning of the presentation, I spoke about some of the market trends. There is a focus from the buying side to look at higher display sizes and quality of displays, providing or the movement to higher resolution sensors provides more granularity in the images, gives the ability to look a little further out, capture more objects in the scene with more clarity. As a matter of fact, as we've heard from OEM, all cameras moving forward for the surround view feature are going to be HD resolution.
Okay, thank you. Another question that we have, and I know that you touched on this some in the presentation, but if you can expand on it perhaps, are there regulations impacting surround view?
So the rear view, which we also consider a subcategory under surround view, it is mandated. So as an example, in the US since 2018, all the new vehicles being introduced are mandated to have a rear view camera. Very recently, there was also something called the Global Safety Requirements Guidelines that came out stating that there is going to be a requirement for some sort of safety feature to be added as mandatory to every new vehicle that's being released by 2023. So yes, there are regulations already in place and more stricter guidelines that are in process of being released to this segment, which are going to drive the adoption and the multiple use cases seen in this market segment.
All right, thank you for that information. Our next question is, why does the market prefer sensor in ISP?
So there are multiple advantages of doing that. For one, if we have the ISP sitting in the camera head, we are essentially providing a complete solution to the end OEM. There is on-chip combination and companding that can happen. It leads to power consumption savings. By providing a more complete solution, it helps reduce the cost as well, reducing the overhead from the OEM standpoint to looking at a more comprehensive image that's being provided for the ECU. So there is system cost savings in terms of SerDes and cabling as well, power savings, cost savings.
Understood. Thank you for that response. And I think we just have time for one more question. And this final question is, why is HDR so critical?
So just going back to some of the images that I shared in the webinar, when we're looking at real life scenes, whether it's in terms of going on an overpass and you're suddenly blinded by the sun, or getting out of a tunnel where you've got a lot of light that's shining on the driver, but part of the vehicle is in the shadows. They're seeing So those are like examples of typical HDR scenes. And to be able to accurately look at the surroundings, to be able to accurately identify objects in these frames with a lot of light and shadow at the same time requires the cameras to have a higher dynamic range. We've seen technologies today that go up to 120 dB, which has become quite a norm now. There are offerings from our semiconductors now that go up to 140 dB, which is certainly state of the art. So in summary, higher the better to be able to capture these real life scenes with light, shadow, all in the same frame.
Okay, thank you, Radhika. And we do have time for just one more question. Do you see the surround view cameras being used in other applications other than cars?
Yeah, we are starting to see an uptake of these cameras in commercial vehicles as well. We've seen it being adopted in trucks. As an example, they have a whole different set of challenges relative to what passenger cars do. There are a lot more blind spots when looking at vehicles, when looking at trucks, especially making turns, especially when looking at these trucks driving in city. So they actually have a lot of advantages looking at commercial vehicles, and we are starting to see that adoption grow as well. That's a good question, by the way.
All right. Well, folks, it looks like we're out of time. For those of you listening to this live or those of you who are streaming it on demand, we do want to let you know that there will be a modified version of this PowerPoint available in PDF form for you to download later on. I want to thank everyone for attending and to give a special thank you to our presenter, Ms. Radhika Arora. Thank you so much, Radhika.
Thank you. Pleasure's all mine.